Welcome everyone to this week's Maritime Innovation Update. My name is Paul Koch. I'm a research associate at the team Maritime Informatics here at Fraunhofer CML, and I'll be the moderator for today. Before we get into the heat, just a few more informations for you. Please note that this is recorded. Also, I would kindly ask everyone to keep their microphones and cameras switched off until the end. There will be some opportunities to ask questions. If you have any questions that you seem very important, you can write them in the chat at any point in time, and we will address them at the end of this presentation. Today's presentation will be done by my colleague Mert Yildiz. Mert studied mechanical engineering for bachelor's and mechatronics engineering for master's, and he will give a presentation on maritime traffic network extraction from historical AIS data using unsupervised learning. And with this introduction, I will hand right over to you, Mert, and wish you good luck for the presentation.
Thank you very much, Paul, for the introduction, and welcome everyone to today's Maritime Innovation Update. So let's start with the presentation. Today I will be presenting you a methodology we created here in Fraunhofer CML for extracting traffic networks. It's a data-driven solution that uses historical AIS data, and as all the data-driven solutions, there is not a best solution to a problem. Therefore, while creating a data-driven solution, it is important to understand the motivation. What did we try to solve with the solution, and how it can help to the big research? For us, while creating this traffic network solution, we wanted to create additional information for vessel trajectory prediction, maritime anomaly detection, and maritime risk assessment. In our researchers here at Fraunhofer CML, while doing vessel trajectory prediction, mostly using machine learning models, the one thing one can easily realize is that it suffers from lack of information regarding the intention of the vessel, where the vessel is going to go. And without knowing this, most of the time it is hard to predict the vessel's trajectory. For the maritime anomaly detection, in order to detect, let's say, heading anomalies or speed over ground anomalies, you need to have an understanding about the normal values in the area that you are trying to inspect. And for the risk assessment in maritime, you need to have a great vessel trajectory prediction and maritime anomaly detection to create an accurate situational picture of the environment. With the navigational traffic that we are going to extract, we want to provide navigational insights for the trajectory prediction models. We want it to understand where the ships can go in the future. And for the anomaly detection models, we want to provide what is the navigation area normals in terms of heading and speed. And for the risk assessment, we want to provide the statistical navigation analysis of the area, where the other ships want to go. And before going into our own methodology, I want to tell you about one common methodology that is used for extracting maritime traffic network, which is using clustering methods such as dbScan. Here on the left side, I choose an investigation area randomly, and I extract the traffic AIS data inside it. This is just cargo vessel data from 15 days or 1 month, I cannot quite remember. And then I directly applied dbScan using some random hyperparameters. It gave me some clusters with different colors, but it doesn't look like anything. Since all the trajectories are connected and different kinds of worlds have different kinds of hyperparameter requests, let's say, the dbScan cannot be simply applied to the whole trajectory cluster. Therefore, what did researchers do? How did they address this issue? They said, if we can do clustering, if we can create at least some very important features of the area, we can create the routes in between or do the dbScan based on that. And what they did is they identified the stopping areas from the AIS data. They simply said speed over ground should be 0 knots, and then they extracted these points, and they said these points must be either ports or anchorage areas. It still gave some outliers in my test data where some ship decided to arbitrarily stop in the middle of the sea. I don't know why. But luckily, the dbScan will get rid of them because it also has a hyperparameter called number of samples. And it gave me the clusters on the right. Now I have my points, and now I can go with creating the grid structure of the world. And I identify the grids that have AIS data inside. And now I have all these points that I found earlier that are represented as a grid, and they are also connected via this grid structure. Now I can use this for trajectory prediction or traffic network understanding. But unfortunately, these methods have some limitations. For example, there can be multiple paths leading between two ports, and this creates ambiguity for trajectory prediction algorithms, such as if you are here, if you are at this crossroad, which route are you going to follow? This can be uncertain. And your understanding of the traffic network is as good as your grid resolution. In some areas, maybe you need finer grids, but maybe they are computationally less appealing. And also understanding the traffic around you, which is one of the biggest problems with this approach. You know where you are going to go, where you want to go. You know your start port, end port, but you don't have this information for the other vessels around you. So when you see a vessel in your close vicinity, you don't really know how they are going to navigate. And much more data and post-processing is needed to create street or lane-like navigation boundaries. So we would have something like Google Maps in that. In our methodology, we start with a simple assumption. There are two kinds of motion a vessel can do in the sea, which is either going straight or doing a maneuver. And the rule to the navigation is two straight legs are connected via a maneuver leg. And also, we assume that just like land vehicles, maritime vessels have lanes that they follow in order to minimize CO2 emission, decrease travel time, or to follow limitations introduced by weather or oceanographic features of the area. And one can start to observe these lanes as the more historical data is visualized. And in our methodology, we extract these straight lines, create an oriented bounding patterns around them, and define this as a straight corridor in which a ship should go in the heading that the corridor dictates it. And in the end, it looks something like this. There are two examples that I created, one from North Sea and one from the Baltic Sea. And as you see, the rectangles are oriented, so I know if a ship is inside that rectangle, it is going to follow, it is ahead. Now I have the bare minimum to create my graph network. In my graph, as you can see on the right side in the animations, ships are following the corridors in an order, and they are connected with the maneuver areas. And I created my graph network by assuming that the nodes are the straight corridors and the connection between them are the maneuver areas. And just by looking at the historical data is enough to understand which corridors should be connected in order to create this graph network on the left. And now that I have my graph network, I have whole new opportunities. I have all the knowledge that I can use that has been accumulated over the years by the researchers on the network optimization. Just to give you a quick example about what it can do, I gave some random start point and destination point, which are shown in green and red. And I used the extracted graph network to find the shortest route that is taking us from the green point to the red using the Dijkstra's algorithm. And this is using only the distance of the corridors, but it can easily be altered in order to use the minimum CO2 emission, for example, or the minimum fuel consumption. The possibilities are endless. And now that I present you a methodology, you might say, okay, it seems like it is working, but is it really working? In order to understand this, we did two tests. First, one of them is we choose an arbitrary area. Again, we extracted traffic insight, and then we checked the AIS reports in this area. Are they really following the corridors that we have extracted? And AIS report is assumed to be following the corridor if the latitude longitude is inside the corridor and if the solar ground of the vessel is aligning with the corridor. And 93% of nearly 100,000 AIS reports that are extracted in this 14-day span is observed to be following the corridors created by our methodology. And of course, if you are making a traffic network, it's a must that you also provide some similar trajectories. And test 2 is regarding that. Here on the left side, the trajectories are clustered by the same color based on their path that is observed according to the historical data. And on the right side, you can see the trajectories that are observed in a corridor, also taken as a cluster. The traffic network can be used to understand shortest route or route planning, trajectory prediction, but in the beginning, I also had the vision to use them for maritime risk assessment and anomaly detection. So now I am going to present you a little use case for the maritime risk assessment. As a part of the LogReview project, I was inspecting the collision model for an offshore wind farm called Budendijk. And here on the left side, you see the green cargo corridors that are around this OWP, and the red one is the closest cargo vessel corridor. And let's assume on this closest corridor, the ship had a malfunction, and it started drifting. And unluckily, the wind direction is also towards the OWP, so it is going to crash into it, drifting with. Of course, the emergency tug vessels can have the distress call and come for help. So on the right side, I show you the positions of the possible emergency tug vessels that are observed from the historical AIS data. And just for the sake of researching, I took the closest one of them, closest one of the positions. I guess it was this one. And then I calculated the minimum drifting distance between the red corridor and the OWP is 4.5 kilometers. And here on the right side, I show you how much time it would take for the ship to drift into the OWP with different wind speeds. And the green line is showing the distance between the closest tug vessel position to the drifting point. So the emergency tug can come and help. And for the emergency tug vessel speed, I assumed to be constant 20 knots. And as you can see, for anything bigger than Beaufort class 2 is going to result in a drifting collision, unfortunately, for this offshore wind farm and for this cargo corridor. Also, this methodology can be used to understand the vessel moment anomaly detections. If we just focus on the heading anomalies or speed over ground anomalies, just by looking at the historical AIS data, I can understand what kind of speeds ships follow in these traffic corridors and what is the heading of the corridor, I already know. And by introducing, let's say, some kind of conditions, the ship's heading cannot be more than 10-degree offset to the corridor heading, we can easily find the anormal headings in the corridors. And in order to create these conditions, we are currently investigating ship collisions from history to see what kind of heading anomalies they had in the corridors that they followed. This will conclude today's Maritime Innovation Updates presentation, and I hope you enjoyed. Feel free to ask questions if you have any, and I will give it back to Paul.
Yes, thank you, Mert, for this very detailed and very interesting presentation, which I think gives a really interesting and in-depth view into our day-to-day work, what we do with the data that we have and what we do with the AIS data. So I would now give the question to the chat. If there are any things that you would like to ask, feel free to write your questions in the chat, and we can discuss them right now. So I see one question is where we got the AIS data from that we have analyzed.
Yeah, the AIS data is from the Danish Maritime Authority, and I used the data between 1st of June and 15th of June for most of the investigation in the selected areas.
I think it's also an interesting information that we have actually quite a big database of AIS data available. And for some limited regions, we have up to, if I remember right, 10 years available to the past of AIS data, which we can use for investigations. Unfortunately, it's a bit limited to area, but yeah.
Exactly.
Another question is if you also included vessel limitations like shift draft, also related to available under keel clearance or ship depth in your graph creation.
I did not do that, but this can easily be done because, as Paul said, we have 10 years of data. And there will be many opportunities that a vessel with the common limitations will occur in this data. And just by looking at them to create a traffic network, to create these rectangles, I can have the traffic specifically for some, let's say, lengths of ships. It is possible, but I didn't do it for this investigation.
And I think kind of a follow-up questions on that was if you also considered vessels nearby the current vessel you investigated, and if it's influencing the heading of the vessel, or what the influence could be.
Yeah, this goes more into the direction of trajectory prediction. I know the other vessel's direction because it will also be following a corridor, because in the end they are all following their lanes. But how many ships you need to consider to understand where your ship is going to go using for the trajectory prediction, that is whole another question that we are currently trying to solve, let's say.
It's under investigations. And I think what also ties into is, I think, the last question for today, which is if we could also utilize this method to investigate near-miss situations, which I heavily agree with is currently not really scientifically, at least, or quantifiably understood in the maritime community. So I think near-miss, yeah, oh, sorry.
Yeah, please finish if you like.
I just wanted to clarify that I think near-miss here now refers to near-miss situations from vessel to vessels, mostly.
Yes, I agree. Actually, I see perfect opportunity to delve deeper into near-miss situations to actually quantify the maritime risk assessment using this methodology. Right now, I was looking actually for a data set that I can use. I found some collision from history that I can use, and I didn't really start getting into that yet, but I am planning to make a research specifically for the situation as well. But yes, it can totally be used to understand the inner dynamics of near-miss situations in different areas of the world between different ships.
I hope that this question is then answered. If there are no more questions, I think we will wrap this up for today. Thank you everyone for joining today's presentation, and be there for our upcoming Maritime Innovations updates. We just posted a link in the chat, which you can follow to register for upcoming events and get notified when we have new presentations, which we'll show you. I thank you all for attending here, and I hope we'll see you next time. Thank you very much and have a nice weekend.